Hi, welcome to the Supplementary Unit on the Properties of Curves, Lesson C, Stationary Points. Today we're going to determine where stationary points occur for a variety of functions. Now you've already seen this before, but not with exponential or logarithmic functions, or even trigonometric functions. So we'll examine a few of these at this moment. Okay, so let's take a look at example 1. Find the position and nature of the stationary points of y equals e to the negative x, quantity x plus 2. So first what we would like to do is, I imagine, we would need to find the derivative. So I'll find the derivative, the gradient function of this, and because we've got two functions here, e to the negative x multiplied by x plus 2, we're going to need to use the product rule. So the derivative of e to the negative x is e to the negative x multiplied by negative 1 multiplied by x plus 2, and then we're going to add that to e to the negative x multiplied by the derivative of x plus 2, which is just 1. Now I'll just do a little bit of simplification here. Actually, sorry, oops, this should be negative 1 up here. I apologize profusely for confusing you there. So we've got negative e to the negative x multiplied by x plus 2 plus e to the negative x. And to make things a little bit easier for us, we'll factor out a negative e to the negative x. And that leaves us with x plus 2 plus 1. Sorry, that should be minus 1 because we're factoring out a negative, and that positive sign will then become a negative. So I'll just get rid of this the best I can here. And there we go. Okay. And now we'll just simplify inside the brackets here. So I'll have negative e to the negative x multiplied by x plus 1. Okay, so from your work with stationary points in the past, you know that they occur. So if I can write this neatly, hopefully I can. Stationary points occur when dy by dx equals 0. So that the instantaneous rate of change of that function at certain points will be 0, meaning there will be a horizontal tangent. So therefore, we have negative e to the negative x multiplied by x plus 1, and that is equal to 0. So if we have two factors and they equal 0, then that means that either one of the factors equals 0 or the other factor equals 0. And with your experience with exponential functions, we realize that negative e to the negative x can never equal 0, so this is undefined. And so the only 0 we're going to have is when x equals negative 1. Okay, so I will here attempt to draw a line with reasonable thickness. And we'll have that will be at negative 1 here. So I will choose values, or a value, greater than negative 1, substitute it into the derivative, calculate that, and see if we get a negative or a positive. So when I substitute in, say, 0 or 1 or 5 or 10 or whatnot, we see we get a positive here in this bracket multiplied by a negative, and so we end up getting a negative here. And that means that the function is decreasing, because this is the rate of change, or the gradient of the function at that point, or that interval. Therefore, the function has to be decreasing there. And when we substitute in a negative value less than -1, we substitute that in here. We get a negative, and a negative multiplied by a negative gives us a positive, which means that the graph is increasing. Therefore, we know that we have a local maximum here, and that occurs when x equals -1. So if we were to substitute that -1 into the equation, the original equation of the function, we see that we're going to get e multiplied by 1, which is just e. Therefore, we have a local maximum at the point 1e. Again, I apologize for my messy writing, but we'll see if we can clean that up for the next example. So for this example, we want to, again, determine the position and nature of the stationary points on the interval from 0 to 2 pi, and then show them on a graph of the function. So here is the function f of x equals e to the sine x. I will take the derivative of this. So we get e to the sine x multiplied by cosine x. And I'll just bring the cosine x to the front here. And stationary points again occur when the gradient is 0, when the derivative is 0. I'll just stationary point occur there. So therefore, cosine x e to the sine x will equal 0. So either cosine x as one factor equals 0, or e to the exponent sine x will equal 0. Again, with your work with exponential functions, hopefully you realize that e to the sine x can never equal 0, so that would be undefined, so we cannot use that. And cosine x equals 0. Well, if we take the inverse cosine x, the inverse cosine of both sides, we end up getting the inverse cosine of 0, which means that x will equal either pi by 2 or 3 pi by 2. That's from prior knowledge of the cosine curve. So now we'll draw a sine diagram. And so we see here that we are at pi by 2 and 3 pi by 2. So when we substitute in values, we'll take a look, we'll evaluate them here. So if I substitute in a value, now it's on the interval from 0 to 2 pi, so suppose I substitute in either 0 or pi by 4 or something easy, and I'll substitute that into the equation here. And I realize that this would be a positive, meaning that the graph is increasing. Then if I substitute in a value between pi by 2 and 3 pi by 2, like pi, into here, I get a negative. Therefore, the graph is decreasing. And then when I substitute in a value greater than 3 pi by 2, we see that, again, it is positive, thus increasing. Therefore, we have a local maximum at pi by 2 and a local minimum at 3 pi by 2. And when I substitute in pi by 2 into the original function here, I end up that the local maximum is at pi by 2 and e, and the local minimum is at 3 pi by 2 and 1 over e. Now what I'll do is I'll actually ask you to then graph that. You can use the graphing software, graphics calculator. You can use Desmos, and take a look at that just to verify that the local maximum and local minimum are at those points. Okay, moving right along.